It's a very good game to illustrate what deconvolution is about. In this game, there is no point spread function, but there's something else which maybe could call bomb spread function. The aim of this game is to find the hidden bombs based on something that spreads around them. So around each bomb, or if you think of macroscopy, each fluorescent molecule, there is a small local pattern, and they combine together, giving you hints of where these bombs are. If we take this and try to translate it slightly towards microscopy instead, if we could construct a toy example where we know the location of the fluorophores in the sample, we would mark them as white pixels. And then we could have a small toy point spread function, not really the ones you've seen before. It's more simple, just a few pixels big. So the positive part here is just 3 × 3 pixels, with the central being 3 and the surroundings being 1. So if we would have this sample, we place it in a toy microscope, we would get something like this. And here I marked the location of the sources with red. Now, the aim of deconvolution is to find back the emission pattern, see where's the source of these photons that we got. So it's to, in some sense, reverse the effect of the point spread function. And that's also why it's called an inverse problem. And in this case, you could solve it by hand, just like in Minesweeper. Because in this case, most of these sources, there are local maximas, but not always. But you could take out the obvious ones first, reduce the pixel values bound, and go one by one, and eventually maybe you will solve it. So that's one way to see it, and I really recommend playing this game a little to get a feeling of how it works, if you haven't. Okay, so the question, why should you deconvolve? Why should you bother about that? Of course, it depends on the modality. It makes most sense where the point spread function is large, such as for wide field imaging. And again, I will give a synthetic example. We will have real data later. I made this small image to the left. It's a volumetric image, and you see one slice. In this one, there are several dots, or what you could think of like fish probes or something similar. One of them is twice as bright as all the other ones, the one I've made this big arrow to. And if you don't believe me, you could adjust the contrast in Fiji, and you will see that it's just that one that is bright. If we now simulate what would happen in a wide field microscope, or what could happen with a certain configuration of objective, it would be that you see something blurry like this. That is fine. That is what we expect. But the interesting point here is that the intensity relationship swaps. So what really is the brightest emitter? Now, if we play with the contrast, it becomes black, meaning that the less intense signals, they look brighter because the out of focus light is enhanced neighbor to neighbor in the denser region. So to make you believe me, I will show you a real data. So I think this is RNA fish. So to the left, there is a big cloud of a lot of signals. And to the right, it's the same image deconvolved. Now you will also probably see some artifacts here. It's not perfect, but at least it looks different. The kind of cloud is gone. What happens if we detect the dots? If we start with the raw image from the microscope, if we look for the local maximas, and here I've encircled the 1,000 strongest ones, so the 1,000 first. And as you see, they have a preference for this crowded region, probably because they are amplifying each other. So the point spread function is overlapping, building up intensity. If we will detect the dots instead based on the deconvolved image, I will show those dots on top of the wide field image. It looks very different, meaning that the deconvolution can have dramatic effects on the analysis later on. And I would like to believe that the bright side here is the more correct one if you're interested in the relative intensity. Okay, so maybe that's reason enough. We will see. But then the other question, if you decided that you want to use deconvolution, how do you do it? What are the steps? First of all, you need to know the point spread function. You need to know it quite well, actually. And typically, there are three ways to go ahead. Either use a theoretical point spread function, so calculated from basic parameters like the Merkel aperture, refractive index, and so on. The basic ones, they are completely symmetrical, like the so-called Born-Wolf model. There are also more advanced models, which have a lot of parameters, and those can be tricky to set. So if your point spread function doesn't look like the ideal ones, you might want to measure it instead using fluorescent beads, small fluorescent beads that are diffraction limited, ideally. And as a third approach, there is the hybrid where you combine a theoretical model and you try to fit the parameters based on the data. And that's also something that is used. So that's the starting point. If you want to use deconvolution, you need to know the point spread function. And that is tricky. I know you've spent some time in the course trying to make everything perfect with the imaging, but there will still be a few things that makes the point spread function a little distorted. I mean, one thing is just the design case, but there's always a design case, and as soon as you just deviate a little from the design case, there will be some distortions to the ideal PSF. And it might look like to the right, where you see it's clearly not symmetrical. Then you have to take care of that. So that's of uttermost importance for deconvolution. Then you need to decide about the method. And I would say, in my point of view, there are two groups of methods. They're either the linear, that assumes a linear relationship between the true image and the what you have imaged, and takes noise into account, and the kind of biggest player there, it's the Richardson-Lucy deconvolution method, which now comes in a lot of flavors with different types of acceleration, for example, but also combined with some a priori information about smoothness, for example. And I think the paper here in the bottom, it's a good place to see just the amount of different methods that are available. And nowadays, and as you will hear later on today, there are also what I call example-based methods that use machine learning or neural networks. These methods typically requires training data. So we need non-deconvolved and deconvolved to train on together, or you will have non-deconvolved and maybe super resolution to build an atlas to see the correspondence between the blurry non-deconvolved and the kind of ground truth images. But we will just look at the Richardson-Lucy method here today in my lecture. And so to give the big picture, what do you need to deconvolve? You need high quality images. That's why you're taking this course, I guess. And you should watch out for saturated pixels and basically everything that deviates from the ideal case. You have to know the point spread function really well. You have to pick a software or an algorithm. And I think you should get familiar with it also. Read about it, because there are always some parameters or some cases that it doesn't handle very well. And one thing you should know is it resource demanding. Can you run it on your laptop or you need to run it somewhere else? And finally, be critical to the results. And sometimes deconvolution isn't the right thing to do. Sometimes you need another modality. And there can be artifacts, as I will show also later on, which you should be cautious about. So that, I think, are the main 4 ingredients. So then I'll just show you some examples, and after that we can go on with the workshop. So I say good and bad, they're mostly quite nice, but I will start with an example which is both good and bad. So here is an image of RNA fish. To the left, it's the raw input image, and to the right is the deconvolved result. And in most cases, it does what you would expect. It removes a lot of the blur. The small signals appear, but there also this thing that looks very weird. Is it a new structure, something we haven't read about in biology? No, that's an artifact. Because here the PSF that was used in deconvolution didn't match the actual points per function of the microscope, causing this artifact. So that's a risk and something you have to watch out for. If there are artifacts, will they affect my visuals or will they not? Here's another example, which I like quite much. So I won't tell you exactly what it is, but I've highlighted a region here, and to the right, you see it now. This is wide field. And if you look in this region, that having a circle, you see it's quite dark. If we deconvolve it, all of a sudden the kind of missing structures appear. In this case, it looks very nice. Most of the cases, things appear that you wouldn't see before. And of course, today in the workshop, we'll use very small images, but it can be applied up to any scale, actually. Here's an example of a 14,000 pixels times 14,000 pixels image, also deconvolved. So it's a whole tissue microarray. And yeah, zooming in, you see it looks sharper mostly. The question then, what about other modalities? For confocal, you can deconvolve. We can deconvolve anything, but with confocal, the points per function is very compact to begin with, so there's no dramatic effect. But you can do it, and here is one example where it looks a little sharper, at least. Also, no obvious artifacts to me, at least. And here's an image I got from Hans, which you met before lunch, I guess. This is STED, and also STED can be deconvolved, and in this case, giving a more point-like structure to the sample. Right. I think my take-home to you will be 2 opposing take-home messages. On one side, deconvolution is great, especially for wide field images where the points per function is large, because it gives pixel values that better corresponds to the emission intensities. But deconvolution can also be annoying because there's a risk that there will be artifacts. There are many parameters and options typically, and it used to take a long time, but nowadays with modern computers, it's not that big issue anymore. And yeah, you will get some experience in the following workshop on this. Thank you.
Good, thank you. Oh, I'm looking forward. We've seen lots of quite impressive images. So before we move on to the to the other Zoom. I want to know if there are some questions. About the lectures. Has anyone tried deconvolution before? Anna-Marie, yeah, Alejandro? Yes. Peru works with STED, so good.
Yeah, but actually I did deconvolution on Eriscan, not with STED. So
Right, yes, that's also part of the Eriscan process. Okay, great. So let's move on to the other Zoom. And bye-bye, people online. We will see you afterwards.